Good morning, everyone. So today we're going to look at VSEPR theory, and I'm going to try to do this in about 10 minutes or less. So let's see if I'm able to succeed in that. All right, so the first thing that we're going to look at, of course, is what this acronym refers to. So VSEPR is the valence shell electron pair repulsion theory, which sounds and looks really complicated, but it isn't. Okay, so calm those nerves. What this is going to give us is a 3D arrangement of atoms around a central atom in a molecule. Okay, so basically what we're going to be looking for are all of the bonding and lone pairs of electrons around an atom. And with that, we'll be able to use the fact that we know that there are going to be Coulombic repulsions between those electron pairs. And with that information and knowing the number of electron pairs, we'll be able to figure out the geometry of our molecule. Okay, so the angles between bonds that occur in a molecule, like something like water. Okay, so in this section, we're going to look at the molecular geometry. It's going to be probably one of the most important. We're also going to look at the bond angles, and then we'll briefly look at the presence of dipole moments in these more complicated molecules. And this is going to be extremely important going into next unit, so keep that in mind. And the very last part of this section deals with the hybridization of the valence orbitals, which I'll explain later. Okay, so starting off, we're going to go super simple. So we're saying that we have two pairs or two regions of electrons or electron density. So in this case, we have two bonds and there are no lone pairs. So the farthest that these bonding pairs can get away from each other is a full 180 degrees. And as a result, that's going to give us a linear structure. Okay, so an example that we have here is beryllium chloride. So we have two bonds, two single bonds, and they arrange themselves in a linear way because 180 degrees is the farthest that they can get away from each other. Now recall that carbon dioxide also has two regions of electron density because they have two double bonds. It will have the same structure as beryllium chloride as a result. The next one that we have is going to be three regions of electron density. In this case, we're looking at three bonding pairs. So boron fluoride is the example that we have here. And the farthest that these bonding pairs can get away from each other is 120 degrees. So the structure that will result, the geometry that we get is called trigonal planar because it's still two-dimensional, because it can arrange in this way, in one plane. So the bond angles are 120 degrees away from each other. But notice that there are three bonds, but no lone pairs. So there are only three regions of electron density here, and that's going to give us the trigonal planar structure. Now, our third basic one is called tetrahedral, and that's going to have four pairs of electron density. So this is actually going to give us a three-dimensional arrangement. So this is our first three-dimensional one, because in order to get the maximum bond angles, we have to go into 3 dimensions. And that's going to give us a 109.5 degree bond angle between each of our atoms here. Right, so the example that we have is methane, so CH4, which has the carbon in the middle and then 4 hydrogens surrounding it. So whenever you're trying to figure out the geometry of a molecule, you need to first draw the Lewis structure, and that's going to tell you how many bonding pairs and how many lone pairs you have around the atom in question. And then you're going to figure out the angles that you'll need to have to minimize the repulsion. So if there's two regions, that's going to be 180. If there's three regions, that's going to be 120. If there's 4, it's going to be 109.5, and so on. Okay. All right. So let's take a look at water. So Lewis structure of water looks like this. So we have 2 bonds and 2 lone pairs. So that means that we have 4 regions of electron density. Okay. Lone pairs and the bonding pairs, they each make up 1 region. So that's going to give us the base model of tetrahedral, right? But keep in mind that we have 2 bonds and 2 lone pairs. So it's not technically going to be tetrahedral because we don't have 4 atoms coming off of here because we have 2 lone pairs. Instead, it's going to give us what is called the bent, right? So anytime you have lone pairs, it's going to give you some derivative of the one that has 0 lone pairs, all right? But you take out 1 bonding pair for each lone pair that you have. So we're taking out 2 bonding pairs for 2 lone pairs. So it's going to give us a structure that looks like this. Okay, and that's called bent. So one little note, lone pairs, because there are no atoms there, so there are no protons to give a little bit of an attraction here. Having lone pairs will actually compress the angles that we have between bonding pairs. So having these two lone pairs here are going to push the bonding pairs farther away from the lone pairs and closer to each other. So this angle here is not going to be 109.5. It instead is going to be a little bit less than that. Okay. So if you're ever asked what the bond angle for water is with this bent structure, it will be less than 109.5. You don't have to memorize all of the specific bond angles for these ones, okay? You just have to know that it's less than 109.5. All right, so here are the VSEPR arrangements for minimal repulsion. So starting off with the 3 that we just looked at, linear, 180, trigonal planar, 120, tetrahedral, 109.5 degrees. But it's not that simple, right? Because we can actually disobey the octet rule for certain molecules. So it's possible to get more than just 4 regions. So in this one, we have 5 electron pairs where, so in this one we have 5, okay? So that is going to give us a trigonal bipyramidal. So we have that trigonal planar. So we have 3 that are 120 degrees apart from each other. And then we have 2 that are perpendicular to that plane. Okay, so that's going to give us the trigonal bipyramidal. So essentially it's the trigonal planar plus 2 extra ones that are 90 degrees away on either side of that plane. Okay. The other one that we have is similar to this, but instead of the 120, we instead have 90 degrees, and that's going to be called octahedral. So we still have the 2 coming out at 90 degrees, but then there's a plane here that gives more of like a square instead of the triangle as a result of 90-degree bond angles. Okay, so what happens if we have lone pairs? Well, that's going to give us a slightly different structure. So for 4 pairs, if it's 4 bonding pairs, it's tetrahedral. If we have 1 lone pair, that is going to give us the trigonal pyramid or trigonal pyramidal. So taking away 1 lone pair gives us this. So again, it's going to be a little bit less than 109.5 degrees between these angles. And then here we have V-shaped or bent, like with the water molecule, if we have 2 lone pairs. Now, for 5 lone pairs, for 5 pairs, if we have 5 bonding pairs, it's trigonal bipyramidal, like we said before. If we have 1 lone pair, so taking away this one right here, that's going to give us a little seesaw shape. So if we were to like set this kind of down on its side, it would look like a seesaw. Here, if we take 2 away, it's going to give us T-shaped. So just take 2 away from that plane So giving 100 and, not 100, 90 degrees between these two, and then 180 between these two. And if we end up having 3 lone pairs, it's going to give us a linear structure. Now, one thing that your book does not have is the octahedral, which you also need to know. So if you take away 1 bonding pair for a lone pair for octahedral, so it means that you have 5 bonds and 1 lone pair. It's going to give us square pyramidal. If we take away 2 bonding pairs for 2 lone pairs, it's going to give us square planar, so just 90 degrees apart from the whole thing. If we take away 3, we're going to have T-shaped again, just like we did up here. And if we take away 4, we'll have linear, just like what we got when we were up here. So again, 2 bonding pairs and then 4 lone pairs. So do you need to remember all those? Yes, you do. As well as the angles too. So that's going to bring us to an example here. So draw the Lewis structures of PCl5, PCl4+, and PCl6-. So, maybe pause the video here and try it out. And then I will come on in a few seconds and give you the answers. So pause the video now if you would like to try this. Okay, so PCl5, we have 5 bonds coming off this with a Lewis diagram. So we know that that must be the trigonal bipyramidal, having 5 bonding pairs and no lone pairs. All right, excuse me. Now, what about PCl4+? Well, now we know that there's going to be at least 4 bonds, right? And since it's plus, that means that we're not going to have any sort of lone pairs or anything like that. So as a result of having 4 bonds, 0 lone pairs, that is tetrahedral. And PCl6-, we're going to have 6 bonds, 0 lone pairs, so that gives us octahedral. Okay, so it's as simple as knowing how many bonding pairs there are and how many lone pairs there are. Then you can really just refer back to this chart and use that to figure it out. Now, are you going to have the chart on the test? No, so it's going to be imperative for you to memorize these. Okay, so now you might be asking, what happens if there are multiple bonds, like a double or a triple bond? Well, in that case, we treat all of the electron pairs that are part of that double or triple bond as one region of electron density, okay? So I am going to use this phrase a lot, okay? One region or one center of electron density to refer to a double or triple bond. So effectively for our VSEPR model, that is going to mean it's going to apply as one bonding area, okay, or one bonding pair effectively. Now, obviously there are several bonding pairs in that region, but for the sake of our VSEPR model, it's going to be effectively one bonding pair, okay? Yeah, and then one more note, if a molecule exhibits resonance, so we could have a double bond in one area and then 2 single bonds, you can use any of the resonance structures to predict our VSEPR structure. Okay, because it means that we're going to still have the same number of bonding areas as well as the same number of lone pairs. So it doesn't matter which one you use. So let's take a look at nitrate. So that's going to be our NO3-. So with nitrate, there are 3 resonance structures. So a double bond and then 2 single bonds. So as a result, there are 3 resonance structures. So what is our molecular structure going to be? We have 3 regions of electron density and there are 3 bonding pairs, okay? No lone pairs. As a result, this is going to be trigonal planar. Okay, so 120 degrees between the 3 bonds. Now let's also try with sulfur dioxide. We're going to predict its molecular structure and draw the dipole moments. Okay, so sulfur dioxide, so we have sulfur, 2 oxygens. So that's going to give us 2 resonance structures, so a double bond and then a single bond, which can swap between the 2 oxygens, and we have a lone pair. All right, so we have 2 bonding pair areas and then 1 lone pair area. So this is going to give us a bent structure. And since we know that we're going to have a bond polarity moving towards the oxygen on both sides as a result in the difference in electronegativity, we know that we're going to have a dipole moment moving up towards the region of the 2 oxygens. Okay? So we're going to need to know this during next unit for sure. So this is a really simple one, but of course we're going to have more practice with this as we move forward. So VSEPR for larger molecules. So if we have a larger molecule like methanol, where we have, it's essentially methane with an alcohol group here. So now we have a carbon plus an oxygen here. We can figure out what the geometry of the carbon is, and also the geometry of our oxygen. All right, so if we drew out the Lewis structure, we would see that there are 2 lone pairs coming off oxygen, and obviously since there are 4 bonding pairs, there are no lone pairs on the carbon. So that's going to give us tetrahedral for the carbon and bent for our oxygen. Okay, so all you need to do is look at the Lewis structure of our entire molecule, right? And you can see the lone pairs and the bonding pairs and figure out the molecular geometry for any atom that you have in that molecule. Okay, so there are 7 questions. I would like you to try them out. Okay, we're going to talk about them in class, but I'm not going to go over them now. So why don't you try them out? So there's 1, 2, it gives you all the answers, 3, 4, 5, 6, 6. All right, and we'll talk about bond hybridization on Tuesday or Wednesday, depending on when we get to it. Okay, that is all for the video for today.